Okay, so we have been discussing some microscopic ideas of what happens when light interacts with materials. Specifically, we looked at situation where an incoming light wave traveling along a certain ray direction excites electrons in a material, electrons that are bound to the atoms, electrons that are free and so on. Does not matter, those distinctions do not matter at this point, it is just a fairly simplified conceptual picture that we are interested in. And based on that, we realize that there are two contributions to the actual field that you look at when light passes through a material, when any electromagnetic wave passes through a material. The first of course is the incident wave itself, the one that is coming from the source, and the second one is the total contribution from the oscillating electrons or from the excited electrons that are moving around in response to the incident field. Now, if you add them up and look at the final field, we saw that there were two contributions. We call this the E full, which had these two contributions, E bar, that is the coming in original incident wave, and the E bar emit, which is the sum of all the emitted waves from each of the electrons in the material. Now, the final E full we said had a phase difference with E, if you remember, and we call this delta, and we said that the value of delta determines how the material responds to a particular light source, a particular type of incoming electromagnetic wave. If that delta was pi by 2, then the wave moves slower, the superimposed wave comprising of those two components is slower than the incident wave. This is what happens typically in a transparent material like glass or transparent polymers and things like that, and it leads to Snell's law, as we will see very shortly, and you get the usual definition of the refractive index and so on. The second case was when delta was pi, then you had complete absorption. So, the emitted field was exactly out of phase with the incident field, and so the total field was 0, which means that you would not see any effective field coming out from the piece of material. So, it is completely opaque. And we also in passing saw that you can get amplification, which is what happens in the case of a laser when the delta is close to 2 pi. Okay. And usually we also mentioned this at the very end with the situation somewhere in between case 1 and case 2. So, you have one transmitting component and you have one absorbed component, and for most practical cases for photoelasticity we will assume that the delta is close to pi by 2, we will not worry about absorption. It turns out for X-ray tomography we will worry about both. Okay. So, the same ideas will hold true when we discuss X-rays, and remember X-rays also are electromagnetic waves, it is just that the frequency is very different from optical light, which is in the visible spectrum. Okay, so then we went on to this question of why light bends, going back to our original question, and I mentioned that there is something called Fermat's principle, you have probably again heard of this before, and it says that light travels along a path such that the travel time is minimized. So, we will look at some of these consequences today, and then we will try and explain from a microscopic picture where this bending comes from and why different wavelengths will bend differently when you have composite light like white light, and consequently why you see fringes, right. That is something we will discuss, and this will naturally lead us to the idea of what is called double refraction or birefringence, which we will discuss in the next session. So, going back to Fermat's principle, this is best illustrated using a very simple example. So, let us say you have land and you have sea, and let us say you have a bird flying like this and it wants to catch a fish that is swimming, right, or that is stationary, let us say it is a stationary fish. Now, let us assume that the bird is like a duck and it can swim as well as fly. So, this bird can give it a beak, this bird can fly faster than it can swim. Typically that is how ducks are, I suppose. And so, how can the bird get to the fish, and presumably the duck wants to eat the fish, right, we will assume that as well. How can it get to this in the shortest time? So, it can travel at a speed VL in land or sorry in the air, this is not land, apologies, the bird is flying, the bird is not running. It can travel consequently, let us call this VA, in air and Vs in water or sea, it does not matter. Now there are a few strategies you can think of. If the bird is extremely hungry and it wants to eat the fish in the shortest amount of time, it wants to minimize its travel time, it can do a few things. The simplest, perhaps the most naive thing the bird can do is, let us just call it point B and point F, B for bird and F for fish, I suppose. The most obvious thing is, okay, it goes straight over here, right. Now you might say, okay, this is a possible solution, but the distance it travels in the sea is actually larger than it can get away with, because its speed in the sea is lesser. So this, it turns out, is not the most ideal route to take if it wants to minimize its travel time. Another option, of course, if you think about it, is to travel as far as possible in the air, because the velocity is highest in the air, and then travel as less as possible in the sea, okay, because the velocity in the sea is lesser. So we are assuming that Va is greater than Vs. So this is one option. This option, which we will call 2, is certainly better than option 1, because the distance you cover in the air is larger, so the time you take equivalently is smaller, but it is still not the optimal solution, right. And so the optimal solution is if it takes a path that is inclined at an angle theta 1 and an angle theta 2, okay. And the optimal path, which I am going to call 3, is when the sin theta 1 by V air is sin theta 2 by V c, okay. If I multiplied and divided this by some constant, let us say speed of bird in vacuum or something, then I would get the expression that corresponds to Snell's law. Okay, so it really tells you that the light that is travelling through these media is actually going in such a way that it minimizes its travel time, right. So it is consistent with Fermat's principle. So now the next question is, okay, why should this happen? Why should it minimize its travel time? And the answer to that is fairly deep, and it is not something that we can get to. In fact, I am pretty sure I do not know the entire answer myself, but let us ask the equivalent question, or somewhat equivalent question, of what happens on the micro scale. Okay. Now remember, the light that is coming in, the incident ray, is actually an electromagnetic wave. So there is an E bar that comes like this, and there is a corresponding E bar perpendicular to the direction in which it travels in the glass. Okay. So this is again perpendicular to this is again perpendicular to this. Excuse me. So the E bar, remember, is always perpendicular to the direction of propagation. So you can't have the same E bar in both cases, they can't be parallel to each other, right. So that is something you want to keep in mind. Now what is actually happening when the light comes and interacts? So this is the interface, of course, and for simplicity again we will just take air or vacuum analogous and let us say glass, okay. The full description of this wave is obtained from a set of partial differential equations called Maxwell's equations. Okay. And in order to explain why this bending occurs, you need to look at Maxwell's equations. We will do that in a second. Before that, I just mentioned one common explanation that is used. It is certainly an explanation I have seen before, but it is not correct. And just to sort of myth bust, we will look at that explanation which is commonly given. So the usual thing that people will usually say is, you have light coming like this, these are the electric field vectors along the light travel along the ray direction, all of them are perpendicular parallel to each other. Let us say it is polarized. So, everything is the same direction for now, we will assume that. And the usual argument that is given is that this is analogous, can be thought of as analogous as soldiers marching, right. So, if you take two such rays and then the soldiers are going like this. So, this is the analogy. They can march faster in the first medium compared to how fast they can march in the second medium, right. So, then the usual explanation is that okay, they come like this and then this guy slows down. So, his speed reduces. So, he does this and then this guy also slows down and eventually this bends, right. This is the explanation I have seen before, and if you think a little bit it does not really make sense, because even if someone were to slow down, there is no reason for them to bend unless this person is going to bend the entire line with them as they slow down, right, and this is not something that usually happens. So, this analogy is not correct. Okay. What actually happens is that the electric field undergoes a jump, okay. And remember the electric field again, because the electrons in the material are all oscillating and they are generating their own field and so on, you suddenly see a jump from this side of the interface to this side of the interface, and this precisely this jump that is responsible for the bending. Now, in order to quantify this jump, you have to look at Maxwell's equations, and Maxwell's equations basically govern electromagnetic fields. There are two variants of Maxwell's equations that are called the free space equations, and then there are what are called the material equations. We will deal with this, not with this. This applies only to free space with isolated charges. With materials, Maxwell's equations are usually averaged over some small volume and then you generate the material equations. It does not matter, for now it does not matter which what the distinction is between them, but it helps to know that there are two versions, okay. So, we will focus only on the E bar field. Remember I said the B bar is always perpendicular. So, whatever the E does, the B will sort of mimic it in a perpendicular direction. So, that is all we have to worry about. And if you do this, there are only two Maxwell equations that are of interest. The first says that the curl of the electric field is proportional to the time derivative of the magnetic field. There are some factors of C and so on, and the units are it depends on what system you use, Gaussian units versus SI units and so on. I will not talk about all that. Just qualitative or semi quantitatively we will try to understand what is going on, okay. So, this is the first one. Notice this has nothing to do with any material properties here. So, this applies equally to all materials. The second Maxwell equation, which you have probably seen before in the form of what is called Gauss's law, is this, okay. This is the charge density on the right hand side. It does not matter what that is for now, for our particular application, and this is called the permittivity. And the permittivity of course is a material parameter. So, it depends on which material you are talking about, and this charge density is like a free charge density. For our case it is 0 because we do not have any free charges floating around, okay. So, these are the only two Maxwell equations we have to worry about. Now if you take the interface and you look at the incoming wave like this and you take the electric field vector, I am going to draw it bigger just to illustrate what I am talking about. You can resolve this vector into two components. You can resolve it parallel to the interface. So, this I am going to call E bar parallel, and you can resolve it perpendicular to the interface. This is called E bar perpendicular. Okay, so, you have this is the original E bar that is coming along at every point in the light ray, and you can split this as E bar parallel and E bar perpendicular, parallel and perpendicular. Now from this, let me call this equation 1 and 2. So from equations 1 and 2, you can show that if the magnetic field is continuous, there is a, since there is a jump in epsilon, remember there is epsilon 1 and epsilon 2, for air it will be 1 and epsilon for the other material. The electric field which obeys 1 and 2 and also has this jump in epsilon is subject to these two conditions at the interface. The first is that the parallel component on the one side is equal to the parallel component on the 2 side. Okay. And the second is that epsilon times the perpendicular component on the one side is epsilon 2 times the perpendicular component on the 2 side. I am not going to derive these because you can apply the divergence theorem from here to this equation, take a small pill box and then you can derive this, you can apply the Stokes theorem to this and get this and so on. So, we will leave out the derivation, but nonetheless this is what it boils down to. So, what this means is that the as the light ray enters the medium like this, the component that is parallel, so this component remains unchanged. Okay. So, if I wanted to find out the vector here into the, and let us say my incident vector is like this is the incident E bar, this is E bar perpendicular and this is E bar parallel. Because E bar parallel remains unchanged, so this will be in 1, the E bar parallel in 2 is the same because of this equation, and the E bar perpendicular in 2 becomes smaller. Okay. The reason is that the equation that we have written down here, if 1 is let us say air, then epsilon 1 is 1, then the E bar 2 perpendicular is 1 by epsilon 2 E bar perpendicular 1, and if I take a magnitude on both sides, then epsilon 2 is greater than 1, and so E bar 2 is less than E bar 1 perpendicular. So, the vector in the perpendicular direction becomes shorter. So, the resultant is actually something that looks like this. So, the incident is all like this, let me just redraw this, so that it is in the same orientation as the vector I have drawn here. So, this vector is like this is the incident, the transmitted guy is parallel to this. So, it is going to look like this. Okay. And not just that, every vector along the light ray is going to look like this and every vector along the light ray here is going to look like this. So, the vector, the light ray which is perpendicular to the electric field is going to be like this. So, this is the net result of the two equations that you see written down over here. Okay. So, the bending of this light is only because of this change in E2 bar. Now, notice also from here you can also derive the fact that the if epsilon 2 is less than epsilon 1, then you have bending towards the normal, and if epsilon 1 is greater than if epsilon 2 is greater than epsilon 1, which is the case we just discussed, then you have bending away from the normal. So, all of this is a consequence of the same thing, right. And the other important thing of course is epsilon is related to the n, the refractive index. So, larger n means larger epsilon and vice versa, and this is related to 1 by v. So, larger v smaller epsilon, smaller v larger epsilon, and the same discussion we had before comes through. Okay. So, the bending to and away from the normal occurs because of changes in E bar perp across the interface. Okay, that is just something you want to remember on a microscopic scale. This is exactly what is happening. Okay. So, now this tells us, if we summarize what we have seen so far. So, refraction basically comes because you have light which is an EM wave of course. So, it has an electric field, the electric field causes oscillations in electrons. Again there are other sources, other means by which an incident light can interact with atoms, there is inelastic scattering and so on, which we will not discuss about all that, but just for our practical purposes we will keep this fairly simple and perhaps a little bit oversimplified, but nonetheless it results in oscillations in the electrons. So, you get an epsilon full which is the superimposition of the incident one and the resulting field because of these oscillating electrons, and the E bar full gives you the origin of the refractive index, and that comes, if you remember, through delta, which usually is between pi by 2 and pi. This is the phase difference between the two components, and it being between these two values tells you how much is transmitted, how it is reflected and so on. The other aspect we also saw is that this bending occurs because of this change in the perpendicular component of E bar, and this explained why something bent towards the normal, away from the normal and so on. Okay. So, now we understand where refraction comes from. So, let us now look at double refraction. We know single refraction, let us look at double refraction or what is called birefringence. So far when we talked about this material piece or sample, I said that you have these, if you remember a discussion from the last session, you have these electrons around these atoms and so on, and then they are oscillating, etc. But we inherently made the assumption that this material is isotropic, and isotropic of course means that all directions are the same. Which means if the light were incident on this phase, let us say you had a cubic sample, if the light were incident on this phase, not normally, maybe I will change the, if the light were incident on this phase like this at some angle theta, or if the light were incident on this phase at the same angle theta, or if were incident on the front face or the back face or any of the side faces, you would get the same response, which means you will get the same n1 sin theta 1 equals n2 sin theta 2. If you assume that this is air, then you get n sin theta r is sin theta I, which is theta here, right. So, I will just call it theta, nothing matters, right, the direction does not matter, but this will change if you have anisotropy in the material. So, a very good example of this is this crystal called calcite. So, if you ever manage to get your hands on a calcite crystal, you will see that it shows different refractive indices depending on the direction. So, for example, a crystal of calcite will have one particular direction, it does not have to coincide with this, it could be this direction for example, in which light coming in or polarization in this direction or electric field in this direction will have a different retardation versus electric field in this direction or electric field in this direction. Okay. The moment you have this, now suddenly the incident direction and remember the incident polarization become important. Direction, okay, we can understand because Snell's law has sin theta and so on. So, the theta matters, but the incident polarization also matters because so far we have been talking about the electric field. Remember, this is the E, this is the direction of propagation. The electric field does not have to be in a fixed direction. Okay. The only requirement is that the electric field be perpendicular to the direction of propagation. If I call this n hat, let us say direction of propagation, the electric field can be in any plane in any direction on the plane perpendicular to n hat. So, if I look from here at this plane, the electric field in principle could go in any direction with respect to let us say some horizontal direction, right. It can go this way, it can be this way, it can be this way, this way, this way, and it can change these directions as a function of time. So, it could be a superimposition of one field like this, one field like this, one field like this and so on. The moment that happens, if you have all directions of E bar superimposed, then that light is not polarized or unpolarized. So, typically light coming from the sun or from some light source is typically not polarized, it is in all the field oscillates in all directions. Now, remember what we said about the refractive index. If the refractive index depends on the direction of the electric field, then depending on what light you are passing in, you will see various types of effects in the light that is coming out. Okay. So, for instance, if the refractive index or if the retardation for electric field in this direction is more compared to this direction, then suddenly you will start seeing that these different polarizations or different E bar directions start splitting away from each other, and that really is what is happening in a birefringence phenomenon. Okay. So, the origin of the birefringence, we will discuss this in more detail, more quantitative detail in the next session, but the origin of the birefringence could be some crystallographic features, for example in calcite. The arrangement of the atoms is such that the E bar emit, right, has some directionality, and that could come because of the way in which the atoms are arranged in the lattice, and so that depends on the crystallographic structure, or it could come because of polymer chains reacting to a load. I am going to put polymer chains in quote. It could also be because of some amorphous, generally some amorphous structure reacting to a load. Polymer chains are a special class of course, but it could be any amorphous structure. And this is what is called stress induced birefringence, and it is governed by something called the stress optic law, which we will discuss in more detail. I am just giving you a sort of bird's eye view of where we are heading with this. And remember that since the E bar is affected, these phenomena will depend, both phenomena and especially stress induced birefringence will depend on the polarization of the incoming light. So, if you remember the demo that we did a while ago at the very beginning of this section on photoelasticity, you had a glass sample and we put it between these two sheets, and then we had a light source and we were looking at it from this side. You could see fringes, right, and remember at that time I mentioned that you have polarizer sheets, and the basic function of a polarizer sheet is to polarize the light. So, light coming from a light source is typically not polarized, it has oscillations in all directions. We will denote that like this, we will discuss this notation in the next session, but basically the light is polarized in all directions. When it passes through the sheet, some directions are absorbed more than other directions. So, light coming in here is polarized, and depending on how it interacts with the material, depending on the birefringent properties of the material, you pick up, you filter out certain other polarizations with the second sheet, and that is what you see in the form of fringes at the end. So, what we will do in the next session is basically set up a framework for analyzing this entire process. There is a somewhat archaic term for this called Jones calculus. I will refrain from using this term because it is basically complex manipulation using complex numbers. This name probably came up in the early 1900s before people started applying complex numbers to many of these things, but there is a very systematic way to manipulate these polarizations and then obtain the final result of what you would expect to see when light passes through the second polarizer sheet. So, all our discussion of photoelasticity will revolve around how you break down this process and how you systematically analyze incoming light, interaction with the material, and then interaction with the polarizer at the end. So, we will continue with this from the next session.